Okay, so this was our last book chapter. That'll do. So we've got this chapter, then Thursday, I guess we're doing randomness and chaos. Tuesday is an open lab period. So next week's Thanksgiving week, so there's no Thursday lecture. It's a holiday. And so on Tuesday, I'll be here in the room, and it's open for you to be here as well. And if you want to work with your group and ask me any sort of questions, debugging or whatever, make use of that time as you'd like. But I won't take any sort of attendance that day. So it's just meant to sort of be a free day for you to have access to me, so I can help out with your projects. And of course, Thursday is Thanksgiving. And then the week after that's the last week of class. And so the week after that, Tuesday will be our final exam review lecture. Wednesday will be when your final reports and presentations are due to Canvas that night. And then Thursday will be stage one of the final exam. Your peer reviews will be due Saturday, and I think I've got a slide at the end here which goes over all this too. And then stage two will be during final exam week. I forget the day that we were assigned for this class. I think it might be Tuesday, but I put it on Canvas and I'll double check that as we get closer. Yeah. It'll be open. It'll be just like the midterm. So I forget which days I'll open it, but it'll be, at least 2 days. I don't know if it'll be Thursday, Friday, or Wednesday, Thursday, or Wednesday, Thursday, Friday, but you'll get certainly at least 24 hours. And I think I'm going to do at least 48 hours. I just don't know which 48 hours it is. So just like the midterm, and then likewise, the final exam will be midterm length, so that stage one and stage two, because it's identical, can fit within a class period. Okay. So any questions about the timeline going forward? Questions online or in class? All right, so this chapter is a nice wrap-up chapter from the book's perspective, where it says, after looking at all of these models, how do we really build confidence and make sure that we're learning? How do we build confidence in our models, use them to update our own mental models, and thereby learn from them? So the kind of common view, I think, hopefully before 212, and maybe now we can reflect differently on this, is that models are, and this is hopefully coming out of 212, we don't think this, but going into 212, if you heard the term models, I think a common view is that models are representations of reality and tend to be useful with someone charged with managing or participating in that reality. So they're meant to be something helping you operate a system. But hopefully then coming out of 212, we see that there are a wide range of models, and that view is sort of on this analog side of things. So there are models that are like that, but there also are models that are not meant for sort of operation. They're meant, I'd say, more for learning. And so, giving kind of an example of that spectrum, we talked about a model, we've talked about this example before. I think a driving simulator like this one is probably not something that, if you're an expert on this simulation, that you're going to be able to drive, be an expert in the real system, but you certainly will be better than somebody who has no experience on this. And so you could view that, on one hand, you might spin out if you got behind the real car, but on the other hand, you're not going to crash and burn. And so you can still learn a lot from a model that is not a perfect representation of the actual system. So one way to view these other types of models over here is that they're kind of better than nothing. That's one kind of perspective. But I think the maybe more optimistic or generous perspective is that they provide a generic and transferable reasoning. And hopefully we've started to see that, where at the beginning of class, if I show you a model of a fishery, it's easy to pick apart all the things that's left out. And hopefully towards the end of the semester, if I look at a model of a fishery, you see all the things that have been intentionally left in to provide generalizable insight over a wide range of fisheries, as opposed to narrow insight on one fishery. So, so basically there's room for both. So there's, what I think Morecroft called hard operations research, or hard OR, which are tools for routine but still important decision making. So, this is right now there's a new field of simulation called digital twins, where you build extremely accurate and precise models of reality, and you constantly take data from reality and recalibrate your model. And so that you've got this model that's kind of running alongside reality, so you can experiment with your digital twin before you experiment with the real system. But they're very costly. They're very difficult to build, and they're pretty much don't give you any generalizable insight on any other system that's similar. They're really meant to be just for that one system. So they're an operational model. Then on the other side of it, what I think Morecroft calls soft OR, soft operations research, are actually tools for making sense of wicked problems. So rather than thinking about how to operate a system, let's think about a generic problem that we see really it's hitting all over the world. What are the key features of this generic problem that make it show up everywhere, even though the local situations appear to be different? And so, this, in that case, we strip out all of the peculiarities that might be needed for hard operation, the day-to-day, and we think about the more generic. That's what we put into it. So, in thinking about this, it reminds me of this cartoon from XKCD, the online comic, where, if you don't know the author of XKCD, if you're not familiar with XKCD, they're kind of these cute sort of geeky comics like this one. The author of XKCD was a NASA engineer who left NASA and does other things, and one of the things is draws these comics, and so he sort of plots this on time. He's taken a lot of physics in high school, got a physics degree, got a job at NASA, and on the y-axis here is how well he understands orbital mechanics, and it climbed over time, but then there was a sort of probably Dunning-Kruger effect where he actually thought he knew a lot and then maybe knew less, and then started playing this game, which is about flying these little ships through gravitational fields and things like that. It's just a game, and then claims that he's probably learned more about orbital mechanics by playing this silly little game than he did through all of these physics courses that he took. And so, this is tongue in cheek, but it's sort of driving home that this model was not for operating the rocket, but in playing with this fictitious world, that maybe you actually can learn a lot to update your own models, so that when you do need to operate the rocket or build the rocket, you have kind of a different perspective. And so, getting back to that book, I really liked Morecroft's little, these diagrams and the story that he kind of built alongside of this. So, if you didn't catch this, but talked about, as a young child thinking about a crude gear system, and maybe in their head you think, I got these two gears, I put them together, and as I rotate one, you might have a mental model in your head that the other one might rotate, let's say, the same direction as the one you're driving here. So you drive this one clockwise, maybe in your head you're picturing the other one also being driven clockwise, so this way and then this way. And then, so just to test that out, you go and actually build a formal model, so a tangible set of gears in front of you, and then you turn one and the other one turns the other way. And at that point you realize, aha, I used the knowledge in my head to build this tangible object that I can interact with. And then, crazy enough, that ends up causing me to update my mental model. And I realize if I turn one gear, the other gear turns in the opposite direction. And so it's kind of this, it's an interesting thing about, it's almost like you learned from yourself, but you learned from the process of building. And so Morecroft calls these transitional objects because they help transition our mental models from one state to another through the process of building them. And that's what he's saying, these simulation models. By building a sim that represents how you think the world works, seeing if the sim operates the way you think it should, and then updating when it doesn't, then you end up transitioning what's in your head. When I read this, it reminds me of some other literature that isn't referenced in Morecroft, but there's this work by a psychologist, cognitive psychologist named Frank Keil at Yale, that has to do with these illusions of depth. And so if you look at this picture here, you see the sun, you see a red sky. If I tell you it's at night, probably doesn't surprise you that there could be a red sky at night. But if I then say, is red sky evidence of good weather the following day? Well, some of you might know the saying like red sky at night or pink sky at night, sailor's delight, pink sky at morning, sailors take warning, or something along those lines. And you say, aha, red sky at night, that must mean the weather the next day is going to be good. And you might look back through your personal history and say, you know, that seems to pan out whenever there's a red sky at night. The next day the weather's good. So I get that, and this isn't a surprising question, and I don't have am I having a good answer for that? But then if I ask you why, like try to explain why is the sky red? That's kind of a hard question. Some people might be able to answer that, some maybe not. And then if I go farther and say, okay, so say you can tell me why the sky's red, can you go further? And if I say, well, how does a red sky have anything to do with the next day's weather? And although you might have been comfortable in this box, I'm guessing that, at least for me, when I moved down into this box, at least this second question in particular makes me uncomfortable, because I thought I understood, when I was in this box. But when you actually asked me to build it, build a formal model where a red sky, like build a simulation where a red sky at night is going to guarantee a good morning, good weather the next day. I don't know how to do that. And when I can't build it, it exposes that I actually don't have the depth of knowledge that I thought I did. I just had an illusion of depth. So similarly, I could show you a picture of low tide here with all these boats sitting out on the sand. And I could say, you know what, low tide follows roughly 13 hours after the previous one. And I don't think anybody would be surprised by the 13 hours. Like, okay, that seems about right. But then if I ask you why, why is it 13 hours? Why is it a low tide and then another low tide? Why isn't it 12? Why isn't it 11? Where's the 13 come from? It exposes that although I'm not at all surprised by the low tide, and I know low tides exist, and I count on them when I'm going to the beach, I sort of might look at the tide schedule. So all of that stuff isn't a surprise to me, but maybe I don't know personally how to explain how this low tide things works. And so asking you to build a model that produces low tide exposes that maybe I don't have an in-depth knowledge of what low tide is. A simpler example is pen. I'm guessing everybody in here knows how to use one of these things. I could hand you a ballpoint pen, you could pick it up, you would know to maybe use your thumb to push that thing down, it'll pop out the pen and you could write with it. But then if I took the whole thing, if I said, all right, here are all the parts to a ballpoint pen, what does each part do? You can probably make some guesses, but things might get a little hairy, maybe with this mechanism up here. So do we know how the ballpoint pen works? Now, if I gave you the parts and allowed you to interact with them, then maybe suddenly you could then fill in those gaps. So if I just say, how does a ballpoint pen work? It might expose you don't have that depth of knowledge. But if I give you this transitional object, this model, and then allow you to put it together in different ways, then suddenly you might realize, exactly how the spring is interacting with the pen itself, how this funny little thing is working, and so on and so forth. And so seeing all the parts out maybe is helpful, but then actually getting to put them together is even more helpful. So I'm not giving you really any more knowledge, but I'm allowing you to interact with this transitional object and afterwards teach yourself how the pen works. So that's kind of the power of these transitional objects. And other sorts of examples here. I know how to set the table. I have no idea why the fork needs to be on the left. So Keil talked about, totally independent of Morecroft, they work in completely different disciplines, would talk about how creating a formal model exposes how shallow our explanatory ability is. So a theory, Keil says, is something that enables a person to engage in an exploration of the world around them. So what he's saying is, if you don't have a theory, you might be able to answer all the right questions, but if I ask you why, you don't have a good answer for that. And so the theory is what fills in, that helps provide that depth there. So the shallows of explanation, another nice phrase that came from Keil's group, is are a consequence of the frequent occurrence of explanations in the absence of theory. So it's easy to say low tide every 13 hours, but without having a theory of how the tides work, then that's really, you can't go much deeper than telling me when the low tides are. And so theory helps fill in those gaps. And I put that together because I really think that Morecroft's formal models and mental models are kind of equivalent to Keil's theories and explanations. So I can't really give you a strong explanation until I build up sort of a theory. And you know, and how do I build these theories? Well, I mean, a theory is, you know, like building a simulation is building a theory. I now have a causal loop diagram. I now have a stock and flow diagram that is my theory of how the mechanism works underneath it all. And once I have that, then I can give you a much deeper explanation than, you know, just reading off a list of facts. So when I hear the word theory, I also hear formal model in my head. All right, so any questions about this general idea of a transitional object? Like, you know, what's the role of simulation? It's to transition our mental models, or as Keil might say, provide theory so that we have to get rid of the shallows of explanation, filling in the gaps. All right, so pretty sort of back to abstract kind of things here. So going back again to the beginning of the class, George Box, all models are wrong, some are useful. Models are defined by how they're used, not what they're made of. You know, so a model, again, my definition of model, good thing to remember for final exam, is that a model answers a what if question. A lot of things can be used to help answer a what if question, not just a piece of math, not just a simulation, you know, a pen broken up into parts could potentially answer that. So thinking about like what we need to put into models, going to the top of this lecture, again, at the beginning of the class, it was easy to pick apart a model of fishery to say it doesn't have all these things in it. And, you know, appealing to totally different discipline, you know, not thinking about simulation modeling, thinking about just knowledge generation in general. You know, if again, theory we're equating with model, we're equating kind of with our simulation models. You know, Keil says the normal usage of the term theory has never required a theory of everything, which I think is very much like the George Box quote, all models are wrong, but some are useful. A theory of how the agent for mad cow disease works does not require us to regress down to particle physics to be a legitimate theory. Like, you can always say like, oh, you left stuff out. It's like in the fishery, we could leave out a bunch of things, and then once you get to what you think is an acceptable level of things, then you ask somebody else and they say, oh, by the way, you forgot about, you know, the wind, or you forgot about the rain, or you forgot about particle physics. And it would be silly to create a model of a fishery that included everything down to the, you know, the viscosity or even lower of that amount of detail, you know, again, into the like the kind of condensed matter physics to make it work. We don't need that to explain what goes on in a fishery, the same way a medical doctor doesn't need particle physics to explain mad cow disease. So it's never a goal to include everything. It's always more important to figure out what to include. And that's always going to be a subset of everything. It's never going to be everything. And what I thought was kind of interesting about it, again, Keil was not, I mean, he used statistics, he was a psychologist, but he did run in the same circles as George Box. But this same sentiment here, I mean, it's a little longer, is basically the same thing that Box said, talking about statistical models. I'm trying to show generality of this idea from generalizing across this thing. And I'm not going to read this whole thing here, but he's basically saying, like, for example, the ideal gas law, PV equals RT, relating pressure, volume, and temperature of an ideal gas via a constant R is not exactly true for any real gas. So it's wrong for all gases. It's an ideal gas law. But it frequently provides a useful approximation, and furthermore, its structure is informative since it springs from a physical view of the behavior of gas molecules. So it's right enough. It is guaranteed to be wrong. The fact that it has ideal in front of it means that it's wrong. My wife was a marine biologist at one point in her life, and she studied, well, so she took classes on invertebrate zoology. And there are so many different mollusks that, I mean, they all have a lot of different parts. And so you could teach about every single mollusk, but you just wouldn't have enough time in the semester. So instead, she learned about the idealized or generalized mollusk. It was an ideal mollusk that had like all of the parts on one mollusk, just so you could talk about all the mollusks at once. There is no mollusk that looks like this generalized mollusk. It was an ideal mollusk or something like that. It wasn't idealized, like as if it, I mean, I guess it's sort of a little bit opposite of ideal, but it was a fictitious one, but it was useful because it sort of said, if you see these parts on a mollusk, that's what they're for. So these are some of the things you could see on a mollusk, even though each individual mollusk will not have all of these things. So that's an example that models are never, it's never the goal to ask, is it true? If truth is to be a whole truth, the answer must be no. The only question of interest is it illuminating and useful? Was it a transitional object? Did it teach you something that beforehand you didn't know? That's what we goal for. So the emphasis here is on building our understanding up, not replicating reality, because we will never be able to replicate reality. Reality is one thing, models are another, our heads are in between. We build models to make our heads be able to deal with reality. We don't build models to mimic reality. In that case, we may as well just work with reality. All right. So now the other aspect of this chapter moves this thing that says about seeking shared understanding. So so I liked this image as well, where he talked about this formal model being a transitional object for team learning. So the cool thing about this is like, you have 4 people on, like, say, your project groups. You all, some of you might be in the Con Bio program, some of you might be sustainability, some of you, you know, who knows, could be in business or something like that. I mean, there's a lot of different ones who have different backgrounds. So you all have different experience that you've accumulated that's really valuable. It's hard to speak with each other, though, because maybe your language doesn't quite always match. You might use the same word for different ways. But if you make a simulation model, we all know how to talk stocks and flows, or we're getting there. So causal loop diagram, stocks and flows. And so now we have sort of a lingua franca for exploring ideas. And so we can put things down and say, I might have a different definition of this word, but how this word works is implemented in this stock and flow. And then that helps define that in a very concrete and objective way to help share and learn from each other. And I didn't mention it in this here, but there's another popular term used in the social sciences called a boundary object. And so we oftentimes simulation models are help us interact on boundaries between disciplines. So a boundary object is something that you can see yourself in, and other people of other disciplines can see themselves in, but it sort of allows for 2 different perspectives to coexist. And so I can see my discipline in the way this object works, you can see your discipline in the way this object works. And if we can agree on this boundary object as something we both can work with, then it allows us to translate across our disciplinary boundaries more easily than language or so on like that. And so having a model or a shared space where we put up data or something like that, and we can work with the data together, that helps us work across boundaries. So transitional object is kind of a term that I like to use when we talk about one-person learning, and boundary object is a term that I like to use. I won't put that on an exam, but this is not a term I created. Like transitional object is something that I only heard Morecroft talk about, but I like it. Boundary object is a term you hear a lot of people use, and it talks about this type of group learning where you put a simulation or something else tangible and shared in between. And that type of transitional object is what a so-called boundary object. Yeah. I would say the game is a transitional object, even though I didn't create it, I interact with it and it helps transition my understanding. A boundary object could be something like I would create with someone else. And so, you know, we could say like, I'm an urban planner, you're a conservation biologist or something like that. Let's build a sustainable city, like in Legos, and then you are going to focus on some things and I'm going to focus on other things. We have to get them to coexist on this Lego model that we're building together. And by forcing them to coexist, it forces us to figure out what our similarities and differences are. And so the boundary object brings two people together in sort of this active experience. No, I mean, again, this is something that I think was defined by Morecroft. And so I'm kind of expanding it a little bit. I think when in this chapter, I think Morecroft's idea of a transitional object was, why do we personally build simulations? And he's saying, I build a simulation to help me understand the system. But I would also argue that even if someone else builds it, your interaction creates something new. Like in the space game, there are trajectories you might fly that no one else has flown before. But by flying these particular figure eights or whatever, then you learn something about, trajectories and simulated gravity or whatever like that. So I'd say the kind of combination of the game as a tool and the trajectory you fly is the transitional object. Just like in the gear example, when I build those gears, someone else made the materials to build the gears, but then I put them together to make the gears to see if I turn one, what direction the other one turns. All right. So those are, again, these are not key things, but I want you to at least have been exposed to the term boundary object. I want you to be comfortable with Morecroft's term transitional object. And it just, I'm mainly just trying to communicate to you that, that the idea here in this class is not that models are meant to be proxies, replacements for the real world. Models are meant to help us understand. And so, and it's really, I mean, this is the key aspect of it. Like, we have our mental database is giant. The database of things in the library is big, smaller than what's not written. And then the numerical database of stuff that's quantifiable is pretty small. So, so this is like, the source of our, like, that's the reason why we need to view simulations not as end products, but as ways to bring people together, because the amount of information across a group of people is far more than any of the information that's actually in a computer model. But if a computer model links people together, then it links their mental databases together, and it makes for much stronger teams. And that's really our goal here. So as you're working on your final projects, I hope you feel that a little bit, as some of you will, feel very passionate about one thing. Other people really care about that, but they're kind of interested in another thing. And hopefully, as you start building the sim, as long as one person doesn't dominate the whole thing, that you at least feel that as you're expressing yourselves through one entity, you find a way to link all of your knowledge bases together and create a so-called community of knowledge, another term that's out there. And this idea of a community of knowledge, I think, is fascinating because it suggests a synergy where the community somehow knows more than the sum of its parts. And in some ways that can be a little bit scary, and I'll give that example in a second, but I think it's generally a positive thing. So this was a paper that after I started teaching this class, my old graduate advisor wrote, where it's a system with a bunch of other people so he was in electrical engineering, but he's working with people in social sciences, in social work. So it's, social work and electrical engineering, you wouldn't think kind of coming together, but in electrical engineering, there's a lot of dynamical systems modeling. Social work is interested in a certain set of problems, and they came together to build sort of dynamical systems models of society. And so this is behind here. I think I've got actually some models from, so like, I'm not going to go into them, but I think I might link to this paper, but there's a causal loop diagram in that paper and a stock and flow diagram in that paper, and they happen to use VinSim. I didn't learn VinSim in grad school. I didn't learn VinSim until I started teaching this course, but I knew dynamical systems modeling. And likewise, I know that my advisor didn't learn VinSim, but I know that The social work community here, I think, did have access to VinSim and was familiar with it. And so he brought some of his background dynamical systems to what they were doing in VinSim. And they built a much more sophisticated dynamical model. So if you open this thing up, again, you'll see causal loop diagrams look just like the ones we build, and stock and flow diagrams look just like the ones we build. And just emphasizing generality, again, these were things that I never learned when I was in college. And that's interesting that when I have learned them to teach them, then I find out my grad advisor is doing the same thing and producing the same sorts of models, which I thought was kind of interesting. But in that paper, they emphasized that this approach required a collective effort of scientists from disparate disciplines working together in a highly collaborative manner for a long period. And they mentioned that in this case, they were focusing trying to understand decisions about drinking, specifically in college students. And so there were a bunch of, there is literature out there about how college students make decisions about drinking, but they were saying that the existing literature rarely considers multiple levels of abstraction is almost exclusively grounded in static linear models. And so, in other words, the model of how someone decides when to drink alcohol does not change over the time horizon of interest. And so it's as if somebody's attitude towards drinking a beer is the same at 4 p.m. as it is at 2 a.m. or midnight or whatever. And they said, that's probably a naive model to assume that there's no dynamic in that process. And so this paper was all about building a dynamical model that involved those feedbacks that build up, peer pressure, et cetera, how that can affect someone's attitude toward drinking if you think about a time scale where things could be changing. And so maybe there's an attitude, maybe someone's attitude towards drinking on a month-to-month time scale is static, but on an hour-to-hour time scale, it's dynamic. And so you can't assume that someone's, that someone who isn't interested in drinking at 4 will also not be interested in drinking at 8. So this is trying to grab that. And they mentioned as this line of work continues, we hope this expands to other groups, and this multidisciplinary method could evolve into a transdisciplinary approach. So using modeling to bring disciplines together was kind of the message there. So I like that message. Again, feeds into this idea of community of knowledge, feeds into this so-called cognitive division of labor. And so what I mean by cognitive division of labor is you say you don't have to be the mathematical expert. If you can find a way to work very well for long periods of time with a mathematical expert. You don't have to be a numerical expert, a simulation person. You don't have to be a social worker. You don't have to be a psychologist. But if you have a boundary object that brings you together, then you can be a researcher that is much greater than the sum of its parts. And that's this idea of cognitive division of labor, that not only can we divide up physical tasks, but mental tasks as well, so long as we have a way to bring people together. And we do this all the time. We don't realize that, like, can one person explain how to build a ballpoint pen from scratch? And my claim is, I don't think so. Like, you could say, if you give me all the parts, I can put that together. But then I can say, okay, but how do you build this casing? And you say, well, it's made of plastic. Okay, where do you get the plastic? You can keep going down. Somebody had to harvest these natural resources from somewhere in order to build this pen. There is not one person on earth that I could say, all right, here, I'm going to let you go in the forest, build me a pen. That required a cognitive division of labor. And, this goes for pencils too. In fact, if you go to B school, and take a supply chain management course, you might read this little pamphlet written in 1958. It's called iPencil. So it's kind of a little funny. It's like, it's not an Apple product, right? It was written in 1958, but it's called iPencil. And it's a pencil's view of its production from natural resources. So it goes into exactly where the graphite comes from, the wood comes from, the little ferrule, the rubber for the eraser, and all of that. And it just shows you that one pencil, to build one pencil, it takes a whole book to go into that. There isn't one person who could build this pencil with all of its components from scratch. I mean, really from scratch, that you'd have to depend on others. And that goes for other things too. Like we fly in airplanes all the time, and most of the time the airplanes don't fall out of the sky, but there is not one person on the planet who knows how an airplane works. I mean, yes, there are people that know generally how the concepts work here. There are people that know how to fly the plane. There are people who know how to repair the plane. But there's one person out there who could build that plane from scratch and fly it safely. And there's not. So it can be a little scary. And I put Lion Air up here for those who remember, it wasn't that long ago, that this illusion of knowledge here, like people thought we understood, these airplanes, but then Boeing, turns out, what's interesting is they had so this is a Boeing 737 MAX. So again, I don't know if everybody remembers, but there was this new model of 737 came out. It had a particular optimization that changed a little bit of how it was structured, but required an update in its kind of control system. But if the pilots weren't retrained on how this control system worked, then they could get into these oscillations, these balancing loops with delays, and actually was a little bit like our escalation behavior. Because what would happen, and we can model this, we could draw a CLD of this and explain exactly what happened here, is that in order to compensate for a physical change, the control system on board would cause the plane to, I think, pitch up. And the pilots that didn't think that should happen, would force the plane down. And so the plane would then try to pitch up even harder. And so you had two balancing feedback loops. The pilot wants to keep the plane down, so they're keeping this thing regulated. The control system is automatically trying to tilt the plane up. And so this is just like your thermostat's trying to keep your temperature here, but the outside's trying to keep your temperature here, and they're fighting each other. And that's what would happen, is that the pilots would fight the control systems, and the trajectories of these planes would oscillate. So they would, so the planes would fly up, and then the pilot would kick in, they'd go into a nosedive to correct, and then they'd tip up even more, and they would oscillate and oscillate, and these oscillations would get bigger and bigger until eventually the plane crashed. And it's exactly escalation behavior that we started out with, in this CLD. And what was crazy about it is Boeing's own simulation engineers already knew this was going to happen. They ran simulations of this in an accurate simulator of the 737 MAX. So using tools like the ones we learned in this class, and they got into these cycles. So they're very predictable, but they submitted them to their managers to say, hey, this control system is not ready to fly because you can get into these cycles. And but the managers, again, had so much faith that we know how to fly these planes, and the pilots are going to be better than one that we're saying that information never made it around, and maybe business pressures or something like that, prevailed. And, a couple of planes crashed, and eventually they had to fix it. And they fixed a problem that was diagnosed in simulation, exactly the way it's supposed to be if you do good simulation work. But they weren't allowing the simulations to help update their mental models, because they weren't using simulations as a transitional object. Then it caused a major problem. So on one hand, I go through this whole example as a case study to say that the illusion of knowledge that comes from cognitive division of labor, on one hand, puts us at great risk because we don't have one person, checking things. But my hope is that you see, in the end, it was actually the failure to make use of our transitional objects that ultimately was the problem. So it's not the community of knowledge that was the problem. It was the breakdown of the community of knowledge that caused this problem. So it went from being a cohesive collective of knowledge to being separate parts. And separate parts, if I go back to the picture, you cut out this communication between these, and then suddenly you go from having an entity that has all of its mental knowledge to having just that entity trying to fly a plane when it's never flown a plane in its life, And so it was the loss of the sim, of the transitional object, of the communication pathway that was the real problem, not the fact that we're leaning on multiple people to build planes. So long as we keep our communication lines open, it's okay. We have these communities of knowledge. The whole human civilization depends on communities of knowledge, but we need to make sure we keep communication lines open and keep talking to each other and have tools that allow us to move out of our stubborn stances so that we can learn and evolve. And that's kind of, I think, what we should learn about the Lion Air case. So any questions about this idea of going from transitional objects to boundary objects? Does this make sense? I see a question online. So our question or comment online. There's a comment online, the boundary objects seem to be related to most universities are moving to interdisciplinary constructs, and comments on how we have a lot of these interdisciplinary science and technology buildings at ASU. And I mean, I would actually say that I think that there's always been this focus on interdisciplinarity. These ISTB buildings at ASU are actually more an accounting thing for flexibility, because ISTB buildings at ASU are not owned by any departments. They're owned by sort of ASU's highest level administration. So at any moment, they can pull someone out of those buildings and put new people in based on need. So when you see new ISTB buildings, it sounds like they're being more interdisciplinary, but really that just means that they're not, that they're more flexible. So more flexible turf. But I do think that the wicked problems that we see require more interdisciplinarity. I'm hesitant to say that we're more interdisciplinary today than we are in the previous day, because once people become interdisciplinary enough, that becomes a new discipline. So you could go back 100 years, and I think they would have been, connecting whatever electricity and art and whatever, and into things that they would view as interdisciplinary, but today would look like somebody studying digital art or something like that. So it's really hard to gauge how things have changed over time, but certainly things are changing, and we need to continue to be talking to each other to keep that up. All right. Okay, so that's the abstract part of the chapter. Now let's get back to a little bit more concrete stuff about we built these sims. How do we actually build confidence that these sims work? And so this term boundary comes up in Morecroft. It also comes up in Keil. I mentioned boundary object is boundary between disciplines. So this term boundary seems to be important. So Keil talks about that theories have scope and more scope and systematicity than explanations, but reach a kind of natural boundary where they tie together a wide range of phenomena in one coherent account that links observables and unobservables. And so the point is this: a model reaches as far as it needs to reach in order to explain a phenomenon, but no farther. So what do you put in the model versus leave out of the model? And that's what Morecroft calls boundary adequacy. And I want to make sure you know that term or understand this idea. Is that are the most important problem concepts inside the model. So did we include all of the right variables? That's what we mean by boundary adequacy. Then there's structure verification. Once you have all of the right terms inside your CLD or your stock and flow diagram, did you connect them? So did you adequately say, okay, A influences B and C, not just B. C influences A and influences B, and also this other thing, D, did you include all of the right structures there? Once you have all that and you put it into your stock and flow model, are your equations dimensionally correct? I mean, I think a common issue we see is when you guys are doing outflows, and a lot of students do it, and they do it every semester. It's always supposed to be population divided by average lifetime, but it's really easy to flip those and say, is it one or the other? Is it population divided by lifetime or lifetime divided by population? And I won't ask people to admit if they've done that before, but I mean, I know several people in this class have done it before, and in every semester I've taught this, a bunch of people do that. And that goes along with dimensional consistency. We know that population and average lifetime are linked to the outflow for a population stock. So that's boundary. We need both of them. Structure, that's the ones that are linked. But did we get the dimensions right? Well, the stock is in units of population. The flows should all have units of population per unit time. Well, I only get population per unit time if I do population divided by lifetime, not the other way around. So that's my dimensional consistency. And then parameter verification. Is the average lifetime in order for me to get my sim to run, I made the average lifetime 2 years. Well, if my sim only runs, if the average lifetime is 2 years, and I'm trying to simulate a human population, there's probably something wrong with my model of the human population, because the human population operates fine with average lifetimes much larger than 2 years. And then extreme conditions. And so this case is, I got my model to work. Can I take the parameters and move them outside of the normal ranges? And does it cause the model to move in the direction? Like, if I simulated a city for an average temperature of, or an average rainfall, like let's say I've simulated a desert for an average rainfall of 8 inches per year. If I then change it to 80 inches per year, do things start flooding like I might expect them to? If I change it to 0 inches per year, do things dry out? If it goes the other way around, and when I do 0 inches per year, things are flooding, and when I do 100 inches per year, things dry out, then I know that maybe something's flipped in my model. So extreme conditions help me see that I accidentally flip a plus or a minus somewhere. So it kind of goes along with this parameter verification. So these are kind of the 5 tools we have to build up our confidence in the model. And so there was this SOAP example that came out of the chapter that I think helps demonstrate some of these things. And so the basic idea here is you got a soap company, which I think was this, the Old English soap or something like that. So this actually, I guess, was a real case study, but they changed all the names just to protect the innocent. But this, I guess, was a real study that Morecroft worked on as a consultant. And the management team here, they built a simple model of their Old English bar's soap volume and their competitors' soap volume. And so there are these 2 stocks, which is kind of like how much soap is being sold to the market. And we're going to lose some of this volume. There's also might trade volume with the competitors. Competitors might lose some of it. And then there's also this competitor of the liquid soap. And so as more people buy liquid soap, then that, they've got people already using bar soap, but then they're trying to see how many people would transition to this liquid soap. And they thought, well, this is kind of a simple model which kind of balances the liquid and the bar soap. And that was their first kind of conceptual, this is it's kind of like what they think they want to capture. But they realized that they were leaving out a bunch of variables that mattered. And of the variables they were leaving out interdependencies that were important. And so to sort of improve the boundary and structural adequacy, then they said, well, in reality, we've got our liquid soap volume up here. We've got a competitor's liquid soap volume. And we've also got an additional liquid soap volume. So there's this, so we've got sort of a bunch of these kind of liquid soap players. We've got our bar soap players that are trading amongst each other. But we also have to realize there's competition between the liquid soap and the bar soap. And so you can't just turn on the liquid soap and affect it and hope it has no effect on the bar soap and vice versa. So you've got to realize there's all of these independencies where you need to add in additional variables and additional connections between variables. The variables you've missed are basically outside your boundary, then you come in. The connections you've missed are structural things that need to be added. So they've made that, which is great, but then they realized that the real system was so complicated that it's not easy to summarize as a stock and flow model here, but they basically needed liquid and bar soap for 2 companies. But in order to really get the dynamics right, they not only had to simulate all of the internal workings of the focal company, but also the internal workings of their competitor to know how they're going to respond. And on top of that, they were going to need to introduce the supermarkets, the Me Too, the generics, on top of that. and have consumer behavior that trades among all of these different things. And so they've got all this stuff that's going on that finally includes just enough variables to the point where we think that if we added more, the model wouldn't be any more useful, but it would just be harder to program. So it'd be harder to fit all of these things. And so that's kind of an example of adding enough until your boundary is sort of big enough to be explanatory, and then making sure you have all the structure. So that's what I mean about adequate boundaries in structure. So before we see how we run this model, I know I'm going through that a little fast, but does this idea about boundaries and structure make sense? Which variables to include, which to connect to each other? Okay. All right, so that's those two. Those are kind of the easy ones. Once we've built the model, then we need to see, like, how do we tune the model and run the model? And so if I zoom in on a simple stock here with its inflows and outflows, then this is an example where I know that the rate, this outflow here, which happens to be on the left, we know its units are in thousands of tons per month. And so these things, when your stock itself is a rate, it becomes really tricky because you get these weird flows that end up having these like time squared things in them. So how do we model bar soap volume? Well, bar soap volume is apparently is a sales rate. How much bar soap do you sell per month? So the stock is itself a rate. So, so that's thousands of tons per month. That's what goes into here. Well, that means that the flow adds an additional per month. So the flow that is going into here needs to be thousands of tons per month. That's the stock. Per month, that's the flow. And my fractional rate of substitution here, this is a constant 0.005, which is proportion per month, or 1 per month. And so this is saying here that the substitution rate, this is how much substitution rate we get for every unit we actually sell. So how much additional soap do we get for every unit we sell here? And if I can see that my rate of substitution is in per month, and I need this to basically add a per month to this one, then I know that my formula here should just be the product of these two, because this stock is already in stock units, and I multiply by something which is in per month units, and that gives me the per month per month. So that's what I mean of try to use the dimensions to guide you in picking the formulas. And that will help you when you're deciding, is it a division? Is it a multiplication? Is it the reciprocal of what I have? Try to use the units. Are there questions about this one? Because this is a little confusing, because the stock is actually already a rate. That means the flow is in sort of a rate per month. It's like a super rate. You know, it's a rate of rate change. It's an acceleration, really. Okay. That's dimensional consistency, making sure all our dimensions check. So then I run the sim, and then I say, well, I've put in all the parameters from the market data that I have. And so this line 1, the smooth line, that's what's coming out of my sim. And line 2, the kind of choppy line, that is what is coming out of the real data. And so I've got real data where I've got these over the 72 months, this is what the growth of this particular product was. And on one, this seems pretty good to me. That's, you know, that's on one hand, this seems good that when I put in the real parameters from the real system and hit run, it started at roughly the right place, which I fixed that, but then it ended at roughly the right place, and it kind of kept close to the real data. So on one hand, this gives me confidence that I've captured some important stuff. But on the other hand, I see these weird oscillations. And any thoughts about these oscillations? Like, what might reflect these oscillations, or what might be something that I haven't included that might explain these oscillations? And that they're not in the model, but they would be in the real system that would create oscillations like this. When we usually think about oscillations, like especially when I talk about months, so this is about 12 months. Here's about 24 months, 36 months is about here, 48 months is somewhere over here, and so on. So this is about a year long right here. If I put that over here, it's roughly around that. So do you see anything like when you think oscillations, what do you think, what's a common cause for oscillations in human data? In business, yeah. Yeah, seasonality, right? The boundaries of the system grew to a point that included a lot of important variables, but none of the variables that I mentioned had anything to do with the time of the year. And so what this kind of shows me is I'm capturing kind of a general trend in long-term growth, but on short-term transients, like, for what people might go out and buy bar soap as gifts or something like that. Like you say, it could be a holiday thing, or there could be some reasons, more people take more showers in the summer. I don't know, but for some reason, there could be a greater use of particular types of soap across the year. And I just haven't included seasonality in my model. Is that a problem? I mean, I don't know. If I'm just worried about long-term market share, probably not. But it is definitely something that is like, there is no oscillations in the sim, but there are these definite patterns in the real world data. So, is that a red flag or not? And, I have to think, well, I could bother to try to add seasonality in my model, but do I really get something out of that? Probably not. All right, so any questions about that example? Okay. Oh, I'm sorry. And then there was a question that delays. So, delays do sort of often cause oscillations here, but then I have to ask, like, well, what's being delayed here? So that would be another hypothesis, is that perhaps these oscillations could be caused by a delayed interaction, but response between the multiple companies. So one company increased surges in market share, which causes a price change in another company, which causes them to surge in market share. And you get oscillations in market share back and forth as both companies still grow. That could be another cause for this. But so maybe this is seasonal, or maybe it has to do with these price wars. But I would think that if there was a price interaction, it probably wouldn't have this kind of 12-month cycle that we see here. So I'm guessing this is probably more consistent with seasonality, but we could build a model, one with seasonality, one with price wars between the soap manufacturers, and see what sort of oscillations we get out. Okay. So the model fits the data pretty well, but is it useful? Can we learn from it? That's sort of the next really important thing to sort of see about building our confidence in the model. And so we call this tests of learning. So we ran the model 3 ways, 1, 2, and 3 here. And so we've got 1 and 2. So 1 is like the background model. We have our company, our competitor, and the grocery stores all together. 2 is our company but without the competitor. So our company, a branded competitor, copies the product innovation. Okay, I said that backwards. So 1 is our company alone, and then 2 is the effect of the competitor now copying us and putting out a competing product. Now, Morecroft says that when he started working with his company, they expected the competitor to be the major risk, that they were going to put out a fancy soap competitor was going to put out a fancy soap, and that was going to eat into their market share a lot. But it turns out that that when the competitors are included in there, the sales volume doesn't change that much. But then they flipped on the grocery stores, the own labels copies it, and the grocery stores are able to produce a lot of the product, the mimicking product, at low prices, and they find out that actually the generics make a much bigger impact on sales volume than the competitor. And so it's that example that was something that they learned here. They did not expect with this simple model, without anything else, they did not expect this level of complexity where they said, oh, turn on the grocery stores and the grocery stores cause everything to tank. They said, we weren't even worried about the grocery stores. We just assumed the grocery stores might have a small impact. But this model showed them that the grocery stores are really going to be something that they need to deal with. Because once the grocery stores start copying, they're going to pick up a lot of market share, and the market share for the brand names is going to start, reducing quite a bit. And so that's an example that they, when a model forces you to update your mental model, even if the model quantitatively isn't that right, if it causes you to make a change in the real world and that real world change works out, it gives you a lot more confidence that that the general ideas were right in your simulation model. So that's kind of how we build up confidence as we're running our models. Does it match the data we have? And when we do something in the model, does it show us something surprising that makes sense to us in retrospect and causes us to learn about the real world by running the sim? So any questions about that? So basically the tests of learning here, and over here, the tests of behavior. So test of behavior, this is when we're seeing if it does what we think it should do, and tests of learning, where it exposes behaviors in the system that we weren't expecting. And although the goal here was to learn about scope, what we're really doing is learning about learning from models. And that's what I'm saying. The tests of learning says is one way we build confidence in models is by having them show us something that we didn't expect. And that helps us, that really tells us this is a useful model, save that model. That makes sense. Okay. All right, so this table I like from Morecroft. I don't think you need to memorize like all of this table exactly, but I definitely think this middle column, tests of structure, is an important one. So these are just common terms and common strategies for running sims. Boundary adequacy, structure verification, dimensional consistency, extreme conditions, parameter verification. These are just, these are the things we focus on a lot in this text and you'll see elsewhere. So I do want you to know, if I asked you the difference between this and that, or be able to sort of, ask you questions about anything in this column, I want you to be able to answer them. But I did want to expose these other columns here. So there's a bunch of different ways to do tests of learning. And there's a bunch of different ways to do tests of behavior, some more quantitative than others. So there's kind of the qualitative, which we do in this book, but in more advanced sims, we actually do goodness of fit tests, things that you might see in your statistical, if you're taking a stats class or you're planning on taking a stats class, learn about things like chi-squared analysis and things like that. And you can have models, sim models, produce distributions and compare them to real world distributions and actually say statistically, via say a chi-squared test, are these things similar or different? And so, but that's outside of the scope of this class. But when you start doing sims for real, then that becomes very important. So, so like I said, this is the kind of the big thing we focus on in this class, making sure we know all of these tests right here. But like I said, there are these more sophisticated ones. So any questions about, I guess maybe I'll say, do these terms make sense to you? These confidence building tests or this process? This is a process you should hopefully see as you're working with your own models as well. And with your own final project models, I definitely think when you run it, you should see, does it behaving correctly? And then hopefully you'll get to the point where you'll find something surprising. And if you do, then it'll say, wow, I really built a cool model if I found something surprising. Okay. All right, so kind of wrapping up here then. I like this this figure that they added in chapter 10. It's kind of like throws in all of the models, most, if not all of the models that were brought up in the book. And it puts them on this spectrum that we started with, between analog, illustrative, and metaphorical. And on top of that, if you look closely, there's two models that show up in two places. Worlds of Showers shows up both under metaphorical and under analog. Why is it in two places? Any thoughts about that? Yeah. Oh, I'm sorry, go ahead. Yeah. Hmm. Right. Right. That's good. So I mean, sort of to summarize that is that like you're saying that in the analog case, this is the we actually care about showers. It's all about showers. We're not learning about anything else than showers. How do we fix this problem in the hotel where the shower down the hall is competing with this shower for hot water? Um, but the exact same model describes a phenomenon that's going on in Harley Davidson, for example, in their manufacturing operations, where they have a limited number of funds that they either can shift to those exporting parts or making motorcycles. And whatever they're currently investing in, supplying the parts or whatever, it's creating a long lead time for the motorcycles. If they're putting capital into motorcycles, it's creating a long lead time for the parts business, and it goes back and forth. So I can leave out a lot of the details, and in the end, the model that I'm using for the showers is just as good as the model to understand what's going on in the business case. So this just drives home the point that that models are defined by how they're used and not but what they're made of. So it's, this world of showers is used in a particular way where, I mean, it's a model in both cases. They're both answering what if questions, but this is asking a very concrete what if question about a real system. This is asking a very metaphorical question about, in general, systems that compete for one pool of resources. So, by how they're used and not by how they're made of. So questions about that, like why World of Showers shows up in both places? Okay. All right, so looking forward, sort of summarizes what I said at the beginning. Due Sunday night, we've got a muddiest point. We've got talk about chaos and randomness, which are two different, very different things on Thursday. Then next week Tuesday will be an open lab. You can work together during that period. Welcome you to come in. I will be here. I'm happy to help you with any problems you're having or help you grow your models or debug things. But if you have other plans that week or you want to make use of the time otherwise, I won't take attendance that day. The last week of class, final exam reviews on Tuesday, then upload by Wednesday night, your presentation videos and reports. Peer reviews will be assigned randomly and due Saturday. Final exam stage 1 will be on Thursday, peer review Saturday. We'll have a final muddiest point, and then that stage 2 exam will be during finals week, just like in the midterm. Yeah. Yes. Peer review is individual. So every individual will be signed a final report and a presentation, not from their group and likely from different groups. And you'll submit that individually. And I will review all the peer reviews, give you a check if you give constructive commentary, and then I will accumulate the peer review scores because there's a rubric. Make sure you fill out the rubric, and then those scores plus my own evaluation will go into the actual grades given to the presentations and the reports. All right. So in that, let's close off an attendance exercise. Again, happy to take any further questions, but I don't want to keep you any later than you need to be. So the question I have here is what type of model adequacy relates to having or choosing variables to include within the model. So there's multiple types of adequacy that we can evaluate our models on. This particular type of adequacy is, did you include all the right variables? What do we call that? Or if the model is a world, what did you put in the world? Otherwise, I will see you Thursday. Have a good week.